late or very early in the morning. So let me first start off by introducing the company that I work for. So Southern Company is a large electrical utility based out of the United States. We have a regulated business operations in the Southeast United States, in Georgia, Alabama, and Mississippi. We also have a company called Southern Company Gas, which operates midstream gas distribution and storage, as well as another company called Southern Power, who is unregulated, and they operate mostly renewables and natural gas combined cycle units across the entire United States. So this figure shows our footprint. We're very wide and wide-ranging. We're, depending on how you measure an electric utility, we're one of the largest in the United States. We, if you look at dispatch or spinning reserve capacity, we're probably the second or third largest in the United States. Lots of customers, lots of employees, 29,000 employees, and we're about 44,000 megawatts of power produced. So I've been with the company for 30 years, and I've seen a very interesting evolution, maybe predictable evolution of our fuel resources and our power generation. So when I first came to the power from the Southern Company, we were about 75% coal. We had about the same amount of nuclear as we do now. Natural gas was a small component, and renewables was a small component. So mostly driven by greenhouse gas reduction goals, the company has evolved to being over 50% generation right now on natural gas at the expense of coal. We're penetrating renewables as much as we can. We're not in a region where I would say renewables are real favorable. There is, solar opportunities. There are some limited wind opportunities. And nuclear has stayed about the same, but we are now building 2,000 megawatts, 2 gigawatts of new nuclear, which should be on in the next couple years. We're one of the few companies in the United States that's actually building new nuclear right now. So we're a little different than most electrical utilities in that we have a very robust R&D program. And thankfully, that's why I'm employed at the company, because I'm in the R&D group. And we research and develop a lot of different areas. We have a renewables group. We have a carbon capture and storage group. We're looking at things like fusion and hydrogen, things off into the future. We're looking at energy storage, midstream distribution, grid level distribution of power, a lot of smart grids, a lot of things we're looking at the company from the standpoint of R&D. One of the biggest R&D projects that we have right now is we are the Department of Energy's contractor and the host site for the National Carbon Capture Center. That is a center dedicated to reducing the costs of carbon capture on electrical generation units. And we've tested more than 60 technologies there. We've collaborated with developers from countries across, all across the world. And we're doing that both on flue gas provided by an adjacent power plant, on coal, and we're now building the infrastructure to do that on natural gas. So we definitely see the need of scrubbing coal plants, but also in the future, since we're hedging so much on natural gas, we want to understand the costs and the technology of capturing CO2 for carbon capture and storage from natural gas. So, like most electrical utilities in the United States, we have developed carbon reduction goals, and that's sort of one of the drivers for a lot of the R&D programs that we have, both directly with carbon capture and storage and indirectly with penetrating renewables. And our goals generally, our goals are to have a 50% reduction from 2007 levels in 2030, and a low to no or net zero carbon emissions by 2050. So that gives us something to look for in our roadmap of technologies to meet those goals. Now, I will say that our near-term goals of 2030 are fairly clearly being met by repowering from coal to natural gas. When you have natural gas combined cycle power generation, you're emitting about 2/3 less CO2 than with coal. So as we slowly shut down the old coal units and build new natural gas units and repower, we're doing a good job of meeting those goals. But between the 2030 and 2050 time range, we're going to have a lot of natural gas and CO2 emissions from natural gas power plants. So we have to work towards either offsetting that with renewables, be net zero by doing something like direct air capture or some other way of becoming net zero, or scrubbing those natural gas plants. So the drivers for carbon management, in the United States, there was a regulation, the Clean Power Plan, in the past, and that was a real driver in us looking at carbon capture and storage. There are carbon taxes. California has a carbon tax. It's a low carbon fuel standard. There's a lot of talk in DC about a carbon tax on power generation, maybe a $50 a ton carbon tax. And then, of course, what's kind of driving most companies right now are these self-imposed corporate goals. Since the Clean Power Plan was kind of repealed in a way, and I won't go into the details of that, but it's no longer a regulation that has teeth in the United States. These self-imposed carbon reduction goals are what are kind of winning the day for the utilities, and it's what's guiding it. And in some respects, I think that's good, because companies like ourselves, like Southern Company, we know what we're able to do and not able to do, and in what time frame. So we set goals that we feel like are commensurate with technology development and with the risk appetite that we're willing to take. So let's talk about secure geological storage. So let's look at the Southeast region in the Southeast United States, where our operating territory is. And I would say that that is one of our attributes with carbon capture and storage. Beyond having lessons learned and firsthand knowledge from the National Carbon Capture Center and being involved in other carbon capture studies, we have what I would consider to be world-class geological storage geology in the Southeast. We've also engaged a lot of research and development with collaborations, including the Department of Energy, who funds a lot of just excellent work in the United States. The Southern States Energy Board, who generally is the people we look to be the prime contractor, EPRI, which is the Electric Power Research Institute, a whole host of universities, national labs, service providers, and consultants. One of our top consultants that we use is Advanced Resources International. We have a very successful record of DOE cost sharing and delivering results. And we have determined through our own studies, as well as studies collaborated with the Department of Energy, that we have significant storage capacity in our region, enough for over 100 years of storage of all of our CO2 emissions. And in many cases, we've demonstrated that a lot of that storage is sitting right directly underneath power plants where we're currently emitting CO2. So if you were to deploy carbon capture at these plants, you would have what I would consider to be low-cost storage, because the storage formations are very good, but also you don't have the element of pipeline transportation at $2 to $3 million a linear mile to deal with. So this good source sink matching is very good. Now, the other thing that I think we have good opportunities for in the Southeast are this concept of regional storage hubs. So if we wanted to pool CO2 from 3 or 4 generating plants, capture CO2 and pipe it to a central location, these geological formations are capable of handling 10 to 20 million tons of CO2 injection per year on an average. So strategically, instead of having storage at each of our individual plants, we may be able to set up these storage hubs, and we're studying that in some studies right now. We have what I would consider to be low-cost pipeline infrastructure development. Now, low cost is, in the eyes of the beholder, but we are able, in most of our service territories, we're able to trench and install pipelines, which is a lot less expensive and easier to do than to blast and go through mountainous terrains or hard rocks such as granites and things like that. And we also have, since we're in our service territory, we have a lot of transmission right-of-ways, and we have built pipelines, CO2 pipelines along, and gas pipelines along these existing power delivery transmission right-of-ways, and we have found that we can generally build these pipelines for less money because of those right-of-ways. We also have opportunities for CO2 EOR, lots of oil companies in the Southeast, and a lot of them are doing EOR operations. And then also several of the Southeastern states are looking at what is Class 6 primacy. So if you're not from the United States, the Environmental Protection Agency has a permitting scheme for implementing injection of CO2 for storage. Well, that there is an option for states, the individual states in the United States, to take over that authority through a primacy application and be the primacy state that where you would deal with your state regulator instead of EPA. Now, we like EPA and we work well with them, but sometimes it's easier to work with your local regulators from each different state than to work with EPA, one of their regions. So that brings me to the Regional Carbon Sequestration Partnership. So one of the biggest programs that DOE has implemented in the United States that has had the most greatest tangible results on defining CO2 storage geology, injectivity, long-term issues associated with storage is the Regional Carbon Sequestration Partnership. And that program was broken up into a series of partnerships. And so it's logical that Southern Company would be a strong proponent and advocate and supporter of the SECARB partnership, which is in the Southeast. So what this program actually did was there were 3 phases. The first phase was sort of consensus building, team building, capacity building, kind of, sort of getting ready to do something phase. The second phase was to actually do some projects in the field. And so we were personally, Southern Company, there were 4 projects that were implemented. 2 of them were coal seam projects in phase 2, and 2 of them were CO2 injection projects into saline reservoir projects. So Southern Company, we were involved in the coal seam project near Tuscaloosa, Alabama, where a small amount, 100 metric tons of CO2 was injected into a coal seam to vet out the potential for enhanced coal bed methane recovery and CO2 storage at the same time. And then we also hosted a site at one of our power plants in Mississippi where we drilled 2 wells. We injected a small amount of CO2, 3,000 metric tons, into a saline reservoir and monitored that CO2 injection in the adjacent well. The adjacent well was drilled just a few hundred yards from the injection well. So that's not a large volume of CO2, but what that project represented for us is that it was the first time we had drilled wells at a coal-fired power plant. It was the first time that we had gotten an injection permit to inject CO2 into a well anywhere. It was the first time that we had injected CO2 into pore space that we own at one of our power plants. So this was like what I would call wading out into the shallow end of the pool. It was doing some things that we knew that we could do, but the fact of the matter is you needed to do them to have confidence to move on to the next step. So the next step, there were 2 projects that were developed in the SECARB program. There was an early test which was performed over in the Cranfield oil field in Mississippi where Denbury Resources and the Texas Bureau of Economic Geology worked on a project where they injected CO2 into the water leg, the saline formation water leg of the Cranfield oil field, and studied that CO2 being injected. And then we developed a project over in South Alabama at our plant Berry, where we built a 25 megawatt carbon capture plant. We supported the development of a 12-mile long CO2 pipeline, and then we injected CO2, that CO2 that we generated from that power plant and captured into a saline reservoir in the Citronelle Dome, in the middle of the Citronelle oil field, but the CO2 injection was in saline formation stratigraphically above the oil field. The injection was around 9,500 feet. The oil field was below 10,000 feet. So we were injecting in saline reservoirs associated with the oil field, but they were stratigraphically above. In this project, again, you can see the pictures. We had the host site, Berry Power Plant. We had the 25 megawatt carbon capture plant, which was Mitsubishi Heavy Industry KS1 advanced solvent capture media. we built the pipeline, or we actually didn't build it. Denbury on shore built it, but we participated in it. 12-mile pipeline, which ran along our transmission right away. And then we did a storage project in the Citronelle oil field, which was managed by Advanced Resources International. So again, this kind of built on our experiences at Plant Daniel, where now we were trucking the CO2 into Plant Daniel for injection. This project, we actually captured CO2 from the coal-fired power plant. We piped it 12 miles. We injected it. There was a permit, and the actual permit was eventually closed out. It was provided a non-endangerment finding by the Alabama Department of Environmental Management, the local regulators. So this project, although it was at a small scale, it's a demo scale, not a commercial scale or a pilot scale, demo scale. We went through all the motions of building a carbon capture plant, integrating it into the host plant, building a CO2 pipeline, injection operations, drilling injection wells, drilling monitoring wells, getting a permit, closing out, doing the injection and closing out the permit. This is the perfect project which allows you to transcend to a commercial scale project. And in fact, the technology of capturing CO2 with MHIA was so successful and it worked so well that technology was scaled up by NRG Energy with MHIA to 240 megawatts. So the engineering scale went from 25 megawatts to 240 megawatts. And that's a logical engineering scale up for a technology like this. You wouldn't want to go from 1 megawatt to 240, but at 25 megawatts, we were able to study the carbon capture plant. In fact, the carbon capture engineers used to joke that what they were going to do is go out and try to break the equipment. They wanted to test it. They ramped it up when the power plant ramped it up. They ramped it down, they shut it off, turned it back on. We were able to study what happens when CO2 is left in the pipeline after the capture operations shut down. We shut down the injection operations to see how that interfaced with the CO2 in the pipeline and the capture plant. So again, that project gave the confidence to this project to be able to scale it up. And that's, as an R&D person, you want to work on things and you want to deploy them commercially. But, the next best thing is for someone else to take that technology and scale it up commercially. And you can bet that MHIA and NRG, we went over and helped them and talked to them about the process, and they came over and looked at the process a lot before they did this. But this is a huge success project. This is the largest carbon capture project in the United States, and actually, I think, in the world right now on coal. So a lot of other things came out of the regional carbon sequestration partnerships. There was a lot of DOE best practices manuals for monitoring, for outreach, for site screening, for risk management. And these things are good. They're very good documents. If you're interested in learning something about public outreach and education for geological storage, if you read that best practice manual, I'm assure you're going to come away from it with a pretty good understanding of how to do that and what the best practices are. And a few other best practices, are operations for storage projects and storage project classification. So these are all good information to have. So after about 12 years, the SECARB partnership, there was a lot of, the project was supposed to last for 12 years. So at the end of it, it seemed a shame to just disassemble all the project teams and all the people that were involved in these projects and all the collaborations and the collaborators and universities and service providers and everybody that was involved in this. So DOE put out a funding opportunity for the 7 partnerships to kind of scale down to 4 main partnerships, but call it a regional initiative to accelerate CCUS deployment and kind of build upon what all the work that the partnerships did. And so this scope of work would be to address key technical challenges, facilitate data collection and sharing, access, transportation and distribution infrastructure, and just promote regional technology. And I think that, and we're into the first year of this, and I think that this is going to be a very valuable collaboration moving forward for the CCS in the Southeast. The other type of topics that we're looking at in that program are, pore space owner and CO2 ownership. Who owns the pore space? If you're doing a large scale saline reservoir injection project, the long-term liability. I personally, and from a corporate standpoint, not too concerned about the long-term liability of CO2 in the ground. I feel like Sally Benson's risk curves that after you quit injecting, your risk drops off dramatically and CO2 starts to equilibrate in the reservoir. I think your biggest liability is right when you start injecting, or, in the first few years of injection. If you're going to find some problems, you're probably going to find them then. Looking at incentives. So, CCS is not cheap, so it's a burden on the people who do it. So there's a lot of tax incentives and different things, and I'm going to talk about the 45Q tax incentive in a few minutes. But, looking at from an industry perspective and a cooperative agreement, a group, a program on what kind of incentives would be best to kind of move this technology along. I mean, for the longest time, the renewables sector got a lot of tax credits and a lot of incentives, and it really spurred the renewables on, in commercial deployment. Eminent domain and easements, you don't ever like to use eminent domain, but, in oil field settings, there's forced pooling and unitization and things like that takes place. So I don't know if we would ever need to do this in the future. And then the state organizational jurisdiction over injection wells. And that's the state primacy thing that I had mentioned earlier. That's very important to work with local regulators and have the people that you're dealing with right there close to where your projects are so they can come out to the projects. Makes everything easy. So, there's in the Southeast and in the United States, there's there are a lot of states that have pore space ownership regulations. A lot of them say that if you own the surface property, you own the pore space, unless the pore space is severed by minerals. Long-term liability, again, while I don't think it's absolutely necessary, a lot of states have some long-term liability protection, tax incentives, and these are not, there's federal tax incentives, but these are things like severance tax and ad valorem tax and franchise tax, things like that. Eminent domain, some states have eminent domain over things like this for building CO2 pipelines and storage, and some don't. And then dealing with enhanced oil recovery laws in a number of states where generally the states have jurisdiction over CO2 injection wells, which are called Class 2 wells in the United States, but not for the Class 6 wells, which are the CO2 storage wells. And so Texas, as usual, they have developed a lot of things that is encouraging. I won't go through all that. Louisiana, they have some liability language in there that they put caps on civil liability cases of $1 million. They have some eminent domain rights. And then Louisiana has announced that they are going to pursue Class 6 primacy, which I think is really good. Mississippi, same way. They have some rules on the books right now. There's some things out there. And then they are looking at Class 6 primacy, which I think is very good. So I'm going to switch gears a little bit and talk about another DOE program that we're engaged in. And it's kind of funny, this is not under CCARB jurisdiction or the regional carbon sequestration partnerships, but it's pretty much a lot of the same partners and the same people. And so the Southern States Energy Board is the prime on these projects that I'm going to talk about right now for Southern Company. And it's a lot of the same partners that worked on the Plant Daniel project and the Citronelle Dome Berry project. But the CarbonSAFE program, and I'm very bullish on it, is that it's a phased approach to kind of demonstrating and developing at the same time the feasibility and developing the infrastructure for commercial scale storage. And so the phase one was called a pre-feasibility study, and it was sort of capacity building, team building, and looking at existing regulations and things like that. Phase two was a storage complex feasibility study. And Southern Company was a part of a project with the Southern States Energy Board where we were awarded about $17.5 million to go out and drill some wells at a site and look at the feasibility of doing carbon storage. I'm going to talk about those in a little more detail. The phase three is site characterization and capture assessment. So that just kind of builds upon the phase 2 study. And we were, in fact, just last week, awarded a site characterization, a phase 3. So we will be drilling more wells and doing more work in that area. And then the phase 4 is infrastructure construction, where you would actually go out and develop injection wells and install pipelines for CO2 transportation for the project. So the phase 2 project, we drilled 3 wells, and these wells were monitoring wells, but they were built to Class 6 standards, which is the standards for the permitting program that EPA has. The contractor that did all that for us was Advanced Resources International. We did a lot of things that you may or may not do in a commercial project, but you know, as long as we're doing it, it's good to have it. So we did a lot of geochemical analysis with Auburn University of what kind of reactions would occur when you inject CO2 into these formations. We did geomechanical analysis, looking at, you know, there are no faults or fractures in this geology. It's very high permeability, high porosity geology, so there's really not any faults or fractures. But, you know, we still did geomechanical analysis of the bedrocks below the injection horizons. Core analysis, we cored all 3 of these wells we drilled, had full core. Cap rock analysis looked specifically at the cap rocks. We did injection and pressure fall off testing. You know, we didn't inject any CO2, but we injected water, so you could translate to what your injectivity would be at CO2. We did a lot of stratigraphy work, and we did a lot of risk analysis. We purchased existing 2D seismic. Advanced Resources International did reservoir modeling. And then we did, you know, what DOE likes to see is technology outreach and transfer. And then we did a lot of publications, and I'll bring just to attention one down here that I was the principal investigator on, that I'll talk about in a minute, about commercializing the site with utilizing 45Q tax credits. So this is just a picture of one of the well locations that we drilled in the phase 2. We drilled 3, and they all look similar to that, although one of them was drilled right on the plant site, right next to the utility boilers, which is kind of makes for interesting pictures. But you'll notice this one was kind of interesting. If you notice the foundation of this site, those are all pallets, because when we started developing this site, we got permission and we got out there and started developing it. We realized that once you dug down a couple feet, you were in kind of a mucky mud, and all the trucks were getting stuck. So we had to lay out pallets across the entire site. But all this drilling went very efficiently. These formations, the penetration rates for drilling was very high. I mean, in a lot of cases, we mowed and demowed in 20 to 25 days on these sites. You know, because the drilling went so quickly, and that included the coring and everything associated, the logging and everything we did on the site. So the phase 3 project, which is the one that was just awarded the other day, is again to drill 3 more wells. So we drilled 3 wells. We're going to drill 3 more wells. These additional 3 wells will be what I would call far field wells. They would be wells that would be looking at this site as from a regional standpoint a little bit more. We know the geology is really good right there at the site. One of the wells we drilled was right on the site in phase 2. 2 of them were a couple miles from the site, or a mile or so from the site. These wells will be a little farther out, because we're evaluating this site not only for storage of CO2 from that facility, but as a regional storage complex. So we need to understand the regional geology. And if we had a footprint of 5 to 10 square miles of CO2 from large volume injection, what does that geology look like out there? On this site, we're actually going to do a real-time 3D seismic survey, which we will go out and run. We're going to be actually doing Class 6 permitting, submitting a Class 6 permit, a Part 1 part of that permit for a permit to inject CO2, although no CO2 will be injected in this phase. We're going to be characterizing deep USDWs, drinking water or potable water sources, and we're doing that mostly for the Class 6 UI permitting effort, Class 6 UIC permitting effort. And then we're going to be doing, now we're starting to integrate capture and transportation techno-economic assessments. So we're looking at 3 other power plants, or 2 other power plants, a coal plant and a gas plant, that are located within a couple hundred miles of this facility, on the economic analysis or the feasibility of capturing CO2 from those plants and transporting it to this location as a regional storage hub. And then again, we'll be doing lots of outreach and education and technology transfer. Now, if you look over on the right, the interesting thing about this site is that there's actually three formations here that represent potential targets for CO2 injection and storage. So when you're dealing with regional storage hubs and you're looking at the large volumes of CO2 and you want to try to minimize the footprint of that CO2, it's best to inject CO2 into multiple horizons if you have that opportunity. Well, we do have that opportunity here, and there's three formations. It's the massive sand of the Tuscaloosa, the Washfred Formation, and the Paluxy, which are all very viable injection targets and seem to have good porosity and injectivity at this point. We know of good cap rocks to where we can inject large volumes of CO2 at this site. So I'm going to switch gears one more time, apologize, but I kind of added this on. I feel very compelled to talk about some work we've done with the 45Q tax credits. For those of you that are not in the United States, the 45Q tax credit is what I would consider by far being the single most largest incentive to do carbon capture and storage. And what it says is that if you capture CO2 at a coal plant or an industrial facility, or a gas plant, and you store it, you inject it into geological formations or use it for enhanced oil recovery, that you will get a tax credit for doing that. And there was an initial tax credit called the Energy Improvement and Extension Act, and then there was a secondary one which built upon it, which was the Bipartisan Budget Act. And so these tax credits, the previous one was capped at 7,500 million metric tons. The Future Act, or the new one, eliminates that cap. So, you know, if you were going to start a project and want to get the tax credit, and you weren't, you know, in a 50% of the tax credit or 60 or 75% of the tax credit in the previous tax credit was already used, you may, you know, get to the cap and not be able to benefit from it. So through a lot of, you know, people talking about that, Treasury revamped that to where they eliminated that cap, which is great. And then it increased the credit. So before, you would get $20 a metric ton for CO2 stored in saline. That is a typo in there. It's amazing how you can do these presentations 100 times and find typos, but it's $20 a metric ton for CO2 stored or not used for EOR. Anyway, I got it right, sorry. Not used for EOR, which would be saline reservoir storage, and then $10 a metric ton for CO2 stored for EOR. So if you're using the CO2 to recover oil, you'd get $10 a ton of CO2 injected. If you were doing it in a saline reservoir, $20. Well, that was increased to $50 a ton for saline reservoir and $35 a ton for EOR. So those are pretty large numbers. Those are you know, good numbers that people are getting people's attention. There's a limit on how much you have to capture, a bottom limit. So for you know, if you're producing power, you have to capture more than 500,000 tons a year. If you're an industrial facility, then you have to capture over 100,000 tons a year. And then the tax credit also goes to the owner of the capture equipment, but it can be transferred. So the one good thing about this credit is that you can transfer those tax credits to anyone you want to, and they could be valued by somebody else. So let's say Southern Company was to go out and do a big project and we didn't need the tax credits one year, we could sell those tax credits or value those tax credits with somebody else. So that we're very pleased that happened. And then it's also, the tax credit is available to direct air capture, which is interesting. So the tax credit is available for 12 years. You can collect it. And so from the date that you put the carbon capture equipment into commission, then you could collect this tax credit for 12 years. So one of the things that we wanted to do was we wanted to do some modeling to look at that tax credit and figure out, okay, how much value really does that tax credit have, and does it offset the costs of capture, transportation, and storage, and under what conditions does it do that? So we set out and we did this this modeling exercise, and we actually published it. So you can see the reference on the bottom there. So the first thing we needed to do was value the tax credit compared to the cost of CCS, right? So CCS is going to cost a certain amount of money at a certain size, and you're going to get a certain amount for the tax credit for every ton of CO2 that you capture in securely geological storage. And then we also wanted to look at the business models and your ability to monetize the tax credits with a third party. We felt like that was very important because, you know, while we don't need a lot of tax credits right now because we've got some renewable tax credits in hand, renewable tax credits are running out. So fossil fuel tax credits may be the thing that we use as a driver for doing this, other than greenhouse gas reductions. And then how the tax credit could change power plant dispatch and revenue. So it's an interesting value proposition. If you're capturing 1 million tons a year from a coal-fired power plant and you're securely storing that in a saline reservoir, that's $50 million a year of tax credit value. Well, I would be hard-pressed to say that the value of the electricity is $50 million a year from that plant. And if you have larger plants, you're looking at, you know, 100 million, you know, 50, if you're capturing 2 million tons of CO2 a year, you're looking at $100 million in tax credits a year. And the fact that you can, you know, transfer those tax credits is very compelling. So what we did was we looked at the business models, and we looked at a vertically integrated business model where, like, Southern Company would do the carbon capture, we'd build a pipeline, we'd manage the injection operations. We looked at a third-party business model where we would do nothing but provide flue gas at our plant gate, right? Someone else would build the carbon capture, someone else would do the transportation, someone else would do the injection. We looked at joint venture and customized, which are similar, but it's sort of let's do it together. So on the joint venture, we would probably capture CO2 at our power plant. Maybe we would transport it or someone else would transport it, and then we would allow an EOR operator to take it and do EOR, and we would get $35 a ton, or we would have a saline reservoir storage operator manage the injection operations, and we would get $50 a ton. Of course, in the EOR scenario, you would hopefully get paid money for the CO2. In the saline geology storage operator scenario, you would be paying someone else to manage the CO2. So, and then there's also a customized business model where we would do some of all the value chain at some level. So we might partner with someone on capture, partner with somebody on transportation, and partner with somebody on storage. So the things that we needed to do was evaluate the operational change for the EGU. We had to understand the cost of capture, right? And that's not necessarily as easy done as said, because there's not a lot of commercial scale projects out there on capture. And then we'd need to know the cost of CO2 transport and saline reservoir storage, and then the value of CO2 for EOR. So we really didn't evaluate EOR in this scenario, in this model that I'm about to present. We basically assumed that we would be getting $50 a ton and transporting and injecting CO2 into a saline reservoir. So we had to calculate the additional fuel and operating costs of CO2 capture. We had to recognize that 45Q tax credits reduce the net incremental cost of operating the EGU. So once you've established the additional fuel and operating costs, you're getting $50 a ton bounty on every ton of CO2 that you capture. So interestingly enough, you would want to dispatch that plant as much as you can, right? So if you were making money off of driving your car, you'd want to drive it as much as you could, right? So you would want to, so the first thing that would happen is that EGU, let's say it was a coal plant and it was only dispatching 50% of the time because natural gas is cheaper, and you could dispatch your natural gas plants at less expense to your ratepayers. You know, by adding carbon capture on there, you might increase, and very well would probably increase, the dispatch of that coal plant. You have to estimate the increase in net revenues and recognize the unit will operate at availability. That's what I just said. And then estimate the capital cost for seeing CO2 capture, transport, and geological storage complex. And then finally compare the net present value of additional revenues, the revenues from the 45Q tax credit, with the cost of installing and storing CO2 from the facility. So this is the kind of the balance sheet on that. And I'm not going to go into this in a lot of detail. It's in the manuscript. I don't really have the time. But what we did was we did use information from Boundary Dam 3, which is a commercial scale carbon capture operation up in, for Sask Power up in Saskatchewan. But the information that we used, the BD3 was a FOAC, or a first of a kind. They did a very, very detailed and an excellent study on showing how on a second of a kind plant of that scale, they could reduce the costs. And so we did the leap of faith, and we're using cost analysis from not the first of a kind, but from their cost estimates on a second of a kind. And we came up with that number, and then we also compared that to some other studies, and they were pretty close. So that gave us a good feeling on that. And this is all based on, I want to mention, a 400 megawatt coal-powered power plant, coal-fueled power plant. We also did the same thing for natural gas. Okay, so we wanted to compare the 45Q tax credit for coal and also for gas. Same thing, 400 megawatts. And now, qualifier here, this has not been done at this scale, or has not been done at any large scale on gas. Now, there's a lot of technology vendors that would say it's a very similar process. You have less CO2 in the flue gas. It's a diffuse flue gas stream, but there's a few inherent differences, but it's basically the same thing. So, there are some cost information out there by GCCSI and the Department of Energy, and those are the numbers we used. So, again, what we're providing here is a recipe for evaluating the value of the tax credit, and we're providing illustrative examples. So, another utility or someone else or another host site would need to look and put numbers into this model, as they felt like were maybe differently realistic than what we feel at this point. So there are inherent differences between coal and natural gas capture. So first of all, natural gas is less carbon intensive due to higher efficiency, so less CO2 to capture and compress. So that word compress is important because compression of the CO2 is a huge parasitic load on the power plant. About 1/3 of the parasitic load of carbon capture and storage comes from compression. So you have, again, it kind of a reiteration, you have much greater CO2 to be compressed at a supercritical coal plant than a natural gas combined cycle plant, making the bare erected costs 2.5 greater for those components for coal than gas. Natural gas has a lower raw water consumption rate, fewer cooling water pumps, which is capital as well as parasitic. And the cooling towers are sized about 2.5 times larger for supercritical pulverized coal. Natural gas requires smaller stripper towers, but likely they would involve a larger absorber tower, right? Because you have less CO2 in the flue gas, so you're going to have a larger tower to separate that CO2 out. And then the other thing that's interesting is the solvent makeup. So this is assuming using solvents as a media for capture. And so the solvent makeup is lower in natural gas combined cycle as related to both degradation and slip in coal systems. And that's still, I believe that to be true, but I still need to, have more evidence of that because we haven't really done this at scale with natural gas. Keeping in mind that we are now just starting here later this year in studies on capturing CO2 on natural gas at the National Carbon Capture Center. And then natural gas combined cycle would not require polishing scrubbers. So most power plants in the United States, well, all right now, and maybe across the world, I don't know, already have flue gas desulfurization in place. But if you were to do carbon capture on it, you would have to have FGD installed because the sulfur would degrade the solvent. So you would have to build that on there. So the other half of this is that we looked at the cost of storage at a site so that we could sum all this up. We got our cost of capture, and we're looking at our costs of transportation and storage. So we use the information from the CarbonSAFE 2 project, and we developed and again, this is all laid out as the costs in this manuscript, but we looked at all the different types of wells we would need, the injection wells, monitoring wells, USDW wells for monitoring drinking water, and we came up with a cost. And so for this 3 million metric ton a year storage complex, we would need about $60 million as capital up front to build this all out. That would be drilling all the wells and doing all that stuff. And then we estimated annual storage, transportation, and operating costs of $2 million for 12 years. So this is the 12 years of the tax credit. And in an annual post-injection, so after you're through injecting, you still have to monitor wells, not quite as much as when you're injecting, but you have to consider that. And we considered a 10-year closure cost for those wells beyond the 12 years of injecting. And so that was about $20 million of net present value. So with all that, and again, one qualifier I have to make here is that this site that we looked at, there were very little transportation costs of CO2 because the formation at this phase 2 project was right underneath the plant site. So this storage complex resulted in CO2 all-in storage costs of less than $3 a metric ton. Now, by anybody's standards, that's pretty dang low. And our studies in the phase 3, by defining that site as a regional storage hub, I'm hoping that we can demonstrate that we can even further reduce the costs of storage below $3, down around $2 a ton, by pooling CO2 in these regional storage hubs. And I think that's one of the values. You know, there's a lot of work that needs to be done to reduce the costs of capture, the parasitic load, and all that stuff, and operation costs of capture. Storage costs, it's really hard to reduce the costs a whole lot because it's really geological dependent. Now, we are blessed with good geology, good injectivity, which results in fewer injection wells, stacked formations, which means maybe fewer monitoring wells because our footprint is less. So there's a lot of inherent things that we look at here. But the interesting thing about this is that through the phase 3 program, the phase 2 and phase 3 program of CarbonSAFE, the value to someone like Southern Company, who's, we're doing this at our plant, would be that it would, beyond understanding our storage formations, it would offset some of the infrastructure costs because all these wells that we're drilling are Class 6 compliant. So we could use these 6 wells as monitoring wells for injection of CO2. So let's get to the punchline here. So the modeling effort on the pulverized coal shows that the discounted, the net revenues that you would get from capturing CO2 from the coal plant, from the 45Q tax credit, would be $1.1 billion, okay? That's a 400 megawatt plant. The cost of CO2 capture and storage would range from 1.2 to 1.3. So, you're not paying off the entire asset with the tax credit, but, it's going a long ways. So the 12-year 45Q tax credit would need to be extended an additional 6 years to total of 18 years, creating $1.3 billion of discounted net revenue to make CCS cost effective in that example. Okay, for the same thing on gas, the discounted $40 million of increased annual net revenues equals $340 million over 12 years. Now, the reason that it's a whole lot less is because of what I said, that when you're capturing CO2 from natural gas, you're getting 2/3 less CO2. So, it's a bigger bang for the buck, if you're looking to get more CO2 because you've got more CO2 to be gotten from coal flue gas. The capital costs of adding CO2 capture and storage for 400 megawatt on that natural gas plant are $500 to $510 million. And so you would need an additional 8 years of the tax credit, a total of 20 years, creating revenues that make CCS cost effective. So, but, the point is, these are, especially with coal, we're using very favorable numbers. We're using next of a kind cost reductions anticipated by people who have the wherewithal to know this, but have not done it yet. We're not including transportation. So if you had to build a 100-mile CO2 pipeline at $2 million a linear mile, you're looking at $200 million. That's not considered in here. And you're assuming that, the tax credit is mature at $50 and that, you're able to demonstrate secure geological storage and get that tax credit. So the next part, and I think this is my last slide, the next iteration, which we've submitted a paper to GHG T15, which has been canceled or postponed till next year, would be to look at increasing the capture rate cost economics. So right now we were modeling out 90% capture. So what would it look like if we captured 95 or 97% of the flue gas instead of 90? So how does the additional costs of going from 90 to 97% capture equate to the additional CO2 captured and the resulting 45Q tax credit? And my, preliminary modeling is suggesting that, my thoughts are that you're probably, due to the incremental capital to do that, you're probably, on good financial ground to do that, to go ahead and capture at greater rates. The other thing is the scale. So can we reduce the cost of storage with storage hubs and reduce the cost of CO2 storage instead of going one-off? And then the other thing is to look at, so the 45Q is a production tax credit. So there's been some proposals and some old investment tax credits in carbon capture equipment that would be on the front end. So, if you were getting the tax credit on the tail end after you built this, that's great. But if you could also get some tax credit on the front end with, capital offsetting capital costs of building this equipment, that's definitely a plus. So we're going to be looking and modeling both the 45Q tax credit and the 48A tax credit. Now, keep in mind that the 48A is only applicable to coal, but who knows? One day it might be applicable to gas at the same time. So that, I am done with my presentation. I don't have the slightest idea how I did on time, but hopefully I didn't go over time.
Okay, excellent presentation, Richard. Yeah, you did good in timing as well. So, and I'm pretty sure that since US is one of the leaders in carbon capture and storage, a lot of other countries can take benefit of this presentation and use the DOE, Department of Energy plans started like a decade ago to develop technologies and knowledge of this topic. It can be actually a model that can be used for other countries to follow the same basically path and advance the technologies needed for this. I've got several questions for you and a few complaints for myself. We got actually notes from 3 countries that I forgot to mention: Argentina, Mexico, and Japan. So I apologize for that, and thank you very much for attending our talk. So some people are complaining about the time, which is actually in some location is exactly the same as time as iftar for Muslims. So for June program, we try to adjust the time a little bit to basically give opportunities to other countries to also participate. So going to the questions. Before that, Richard, actually, forgive me, I forgot to ask your permission to record the session. So I did it anyways, but I only publish it if you permit me. So just let me know. And
yeah,
also,
that's fine.
Oh, that's fine.
Yeah.
Okay, perfect. So everybody, you will have the recording by tonight, or let's say tomorrow on our website on the training tab. Richard, also, we usually share the PDF version of the presentation if the presenter basically wants to do that. So it's another thing. If you want to share it, just send me a PDF copy, please. Okay, so going to the questions, let me start from the beginning so I make sure I don't miss anything. So, okay, oh, you got actually many questions. So the first question is from Annapurna. What are the geological requisites for CO2 sequestration?
Okay, yeah, that's a good question. So you've got to have a formation that can store the CO2. So you must have porosity and permeability. You need to be able to inject the CO2 into the formation. So formations that are generally good are sandstones, have that injectivity and pore space. And then you also have to have cap rocks. So you have to have a geological scenario where you have injection formations which have porosity and permeability, but have rocks on top like shales or chalks or dolomites or something like that that are impermeable, so the CO2 won't tend to come back up into shallower formations. The whole essence here is to keep it in the ground and not allow it to come back up into drinking water sources. So that's basically the geological framework, and those framework exists extensively around the world, and surely very predominantly in the Southeast United States.
Great. Richard, you actually answered partially the next question from Integrity Institute about the caprock, but they also ask how do you assess the caprock and to what regional extent?
Yeah, that's a great question. So I love to answer this question because, so what we did was when we had the Plant Daniel project, we had a public notice meeting, and this lady walked up to me and she goes, I understand, that you guys are saying that these geological formations are easy to inject the CO2 in and you can store it in it, but you don't have a sequestration site unless you have a good caprock. What are you guys doing to evaluate the integrity, the long-term integrity, and the geochemical integrity of those cap rocks, over long periods of time that this CO2 will be in the ground? And honest with you, we had done some preliminary testing on those cap rocks, some unconfined compressive strength. We had cored one of them and did some basic kind of the run-of-the-mill permeability analysis from, some of these commercial oil and gas labs. I didn't really have a good answer for that question. And to me, it was obvious that the cap rocks were good, and it was shale, and we all know that most shales are very impermeable. So we developed a cap rock lab. I funded a cap rock lab at the University of Alabama at Birmingham, which was a specialty lab that only would run analysis on cap rocks. And so any of these projects that we've done, we've always collected some. We've made sure that we drill through or get part of the cap rock. You don't necessarily want to drill through the cap rock in a lot of locations, right? Because you don't want to compromise the integrity of a site that you'd be looking at. But we would try to drill so that we did get some of the representative shales in the area and run those through this. It was a lab setup that it would take, it would run for months, where we would slowly infuse, nitrogen or inert gases. And we did actually do it with CO2 into the cap rocks and look at how long it would take for them to permeate through those cap rocks. And in many cases, it was hundreds and thousands of years that the results would come out.
Okay, thank you. Fushan is asking about the evaluation assessment that you have done for your project with respect to CO2 injection risks, such as seismicity and CO2 leakage, right?
Yeah, to me, the most vulnerable you are on a carbon storage project is leakage from the wells that you're drilling, okay? Or if you've improperly cemented them, or from legacy wells, if you're working in an oil and gas environment, wells that you don't know that are out there, and suddenly, the CO2 plumes hits these wells. So I do think that we need to have you know, looked at this, but we need to have ways of being able to understand, you know, if CO2 is leaking somewhere in a legacy well that we don't know about, we need to be able to identify that. And then there are some technologies like LIDAR and soil flux monitoring and things like that that you would do. But frankly, looking for vegetation that might be, stressed from the CO2 emissions might be the easiest way to go. But surely, you know, making sure that you have very well constructed well bores that you're drilling with your cementing and doing your mechanical integrity logs and things like that. I don't worry. I think if a site is properly characterized, that I really don't worry about that site having leakage through the geology or induced seismicity. We don't have a big issue with induced seismicity in our service territory because we're dealing with a lot of unconsolidated and semi-consolidated sandstones that have Darcy, you know, permeability and 20 to 25% porosity. I mean, we're dealing with some formations that, you know, that are not going to be pressured up. They're regional storage formations that some of them extend, you know, across state boundaries for hundreds and hundreds of miles. So in fact, the formation that we had injected at Plant Daniel for the pilot injection, the Tuscaloosa formation, is one of the formations like 150 miles north at Kemper, at the other site where the phase 2 and phase 3 CarbonSAFE was. It's the exact same formation. Now, it's a little different, it's a little shallower, but these formations are regional saline formations. And also there's limitations on injection pressure with CO2 injection permits, so you don't fracture any of the rocks.
Richard, you got a relevant question in the same way from Alan, asking about specifically what technologies would you like to see to improve CO2 monitoring, actually subsurface?
Yeah, I mean, it obviously helps a project to have fewer. Excuse me?
Oh, sorry, it wasn't noise. Would you please mute yourself, gentlemen, because we have noise from your side. Oh, let's see if I can do that. Okay.
Okay,
sorry.
yeah. So, yeah, I mean, I'm not an expert on CO2 monitoring, but I've been around a lot of projects, and we have used, you know, cross seismic and vertical seismic. Those are expensive. We've done pressure and temperature monitoring. We've deployed monitoring tools, fiber optics and things in wells. It helps a project. That is an aspect of carbon storage that would allow us to reduce the costs of storage by having fewer monitoring wells and not having to have, you know, direct, you know, fluid sampling or pressure and temperature monitoring in individual wells. But I really can't speak to, you know, right now I think there's a pretty good suite of technologies to monitor CO2, but I think that there are probably improvements, you know, that could be made. And I think DOE is definitely funding projects and looking at things that could be used.
Thank you, Richard. Just to complete what you said, actually currently DOE is open to new ideas or combination of current technologies to basically improve subsurface monitoring. And I'm saying that because Petrolern is heavily involved in that. So if you have any idea of combining different sensors and or some idea quite, completely new, the Department of Energy is quite actually interested to fund this type of projects, just for your information. So I have a question from Petrom, which I'm sure everybody likes to hear the answer from you. And is with respect to the capacity of the carbon capture and storage to generate job for people. Is CCS really a job, market for people?
Well, I mean, it hasn't taken off like, you know, I had hoped it would as a technology developer and a researcher. There are some commercial projects, but more and more, I was just seeing some jobs on the websites and then on LinkedIn just recently of jobs in this area. But I'm very optimistic that the 45Q tax credit will stimulate commercial development, and with commercial development, there'll be jobs. It's just going to have to, right now there's only a finite number of projects that are taking place, and a lot of those are DOE funded and DOE kind of incentive projects. So I'm hopeful that the 45Q tax credit, I know there's a lot of projects that have been proposed right now, and there will be a lot of jobs that will be developed with those projects. But a lot of those projects now, with the kind of the whole thing with COVID-19 and the economy, they're kind of being tabled for now. So I really think we're going to have to wait until the first part of next year and see where things are going with the technology. But I'm hopeful.
And thank you, Richard. So next question is from Idoko, asking what area of CCS would you advocate for research studies for like PhD students to work on it?
So on capture and storage, or just
CCS, probably capture and storage both. Yeah.
Yeah, I think capture. I think we really, storage is doing things that we've kind of already done, and we're just improving on it. The oil and gas industry has been injecting CO2 for EOR. The oil and gas industry has drilled wells to look for oil and gas. The same sort of things that they're doing, we're just. Okay.
And Richard, whenever you get tired of questions, just let me know. We can stop at any time, but there's several other questions still coming. So regarding wellbore integrity, Nadia is asking, how did you assess wellbore integrity?
I'm sorry?
So the question is that how was wellbore integrity assessed?
Oh, we've moved. Okay, we're on another question. Okay.
Yeah. I just ask you if when you are tired of the, answer you, or you don't have time, just let me know to stop asking the question. So
yeah, no, we're good. We're good.
Okay.
Wellbore integrity, you do the mechanical integrity tests when you first drill the well and cement the well, and then you're required by law from the state regulatory agencies to do mechanical integrity tests. And some states are every 3 years, some states are every 5 years. So you would go in and assess those wells that you're using, but the thing about that is that if you're doing injection operations to do the mechanical integrity tests on your injection wells, you have to have backup injection wells so that you can shut down your injection wells, do those integrity tests, and then bring them back online.
Okay. And we have some question about the seismic, basically monitoring and seismic data. Which processing method do you use or planning to implement basically to process the seismic data? Is it P.A.S.S, depth migration, or FWI?
Yeah, I wouldn't have the slightest idea. You're getting way out of I'm more of a project.
I would say that.
You'd probably be able to answer that question better than I would.
No, I'm not a geophysicist either. I don't know if there's someone. Alan, can you answer this question? Because I know you're geophysicist by background. Alan, are you still there? No, I think Alan left. Okay, so let's move to the next question. Al is asking about geochemistry, how to enter this topic with the help of geochemistry. What's the application of geochemistry?
Yeah, so what we did was on our projects, we've generally had a geochemist who would take some of the core that we collected, and they would do experiments on, the interaction of the CO2 with the minerals that are in the geological formation. So a lot of our geological formations are highly siliceous. They're composed mostly of silica sands, and there's not a lot of carbonates and things like that, or other accessory minerals. I mean, if you had, you know, the scenario here, the worst case scenario is that you have a formation that has a lot of mineralogy, and when you inject CO2, the CO2 mixes with water, then mixes with the formation, and then gets into the minerals and reacts and clogs up your porosity and permeability, so you start having problems with injectivity. We tend not to have that problem in the Southeast because, like I said, you know, silica is very, you know, chemically inert. It doesn't react. So we don't have that type of issue, but we still have studied it on these projects looking at that. Now, if you were doing injection in areas where you did have more carbonate geology or accessory minerals, I think the geochemical analysis is very important.
Okay, and Roy, I think is asking a question from university sides, and there's how academia can get involved in CO2 storage projects.
Well, the best thing to do is to try to get in touch with industry like Southern, like ourselves. I'm happy for anybody on this call to reach out to me and look for areas of collaboration. But the biggest thing that we kind of lack right now is having projects where we're actually injecting CO2 in the ground, to where we could do research studies along with those. I mean, you know, if I was commissioning a commercial scale CO2 injection at a site, I would, you know, love to collaborate with a whole host of universities and collaborators on doing studies with that CO2. One of the most interesting kind of studies that I have seen in a long time was in Germany with the Kretchen site, where they injected CO2 and then they waited, you know, 3 or 4 years later, they injected a finite amount of CO2, and they went back and drilled into those formations where they had injected the CO2 to look at how that CO2 had geochemically reacted with the formations, how much pore space had that CO2 occupied in that formation, and how far it had exactly gone with these ancillary boreholes. I think academic studies like that would be very helpful to deploying commercial scale projects.
Okay, and question from Mahdi: have you experienced any mechanical failure of saline reservoir during carbon storage?
Mechanical failure of the actual reservoir, like induced seismicity? Is that what
it's not actually clear to me, but if so, what are the implemented red light strategies? Have any of the geomechanical studies pointed out to a probable failure? It is probably failure of the faults and fractures, I guess.
Yeah, I mean, yeah, you got to be concerned with that. Induced seismicity and reactivating faults is a big deal. You know, but I do think that in a lot of respects, faults are kind of misinterpreted. A lot of faults are not active, and they've been sealed. And in fact, you probably could inject in proximity to a lot of faults and not reactivate those faults, but that's going to be a public perception thing and maybe not a thing. You know, EPA is going to be very stringent on where they allow commercial scale storage to take place, and they're probably not going to permit a site if you have a bunch of faults running through the site. I mean, that's probably going to be a non-starter. There's been some theoretical studies that have taken place. There's been a group, I think the CO2 CRC in Australia has looked at, you know, studying the impact of CO2 injection on faults. The Texas Bureau of Geology has done some work on that. Again, that's not something that, you know, and this is just not from an industry-wide perspective, but from my, you know, hometown perspective, we don't have a lot of fault-riddled formations in the Southeast that we're dealing with. It's all coastal plain sediments, it's sandstones and shales and geological formations like that really don't have, they might have bedrock faults deep underneath these formations, and you would have to be cognizant of reactivating bedrocks, which could cause an issue, but keeping in mind that the CO2 wants to rise. So you're really looking to, you know, for the integrity of those cap rocks and not creating, you know, any type of fractures or faults in those cap rocks.
Okay, Richard, I can see that your presentation have been really attractive to people. I'm not going to take advantage of you being very nice to us. I'm going to select 2 more questions among, I think we have 15 more questions, which definitely we don't have time for it. I select 2, and then what I would...
Please feel free to pass out my contact information if people want to reach.
What I'm going to do, because we don't want to blow out your email, I will send an email to you with the questions that has been left. So you answer to us, and then I will share it with everyone. Is it good?
Okay, that's fine.
So let's go over 2 more questions, and then we close the session. So question is that after the 10 years of monitoring post shut-in, does the liability of monitoring transfer to the state?
Yeah, so that's a good question. It depends on the state. So there are some states like Louisiana that will take on a certain amount, I think it was up to $1 million, of the long-term liability of the site after it's been closed out. But my perspective on the long-term risk liability of CO2 injection is that, again, after you are through injecting, your risk profile drops down dramatically because the pressure gradient, there's no injection going on, you're going to have equilibrium going out. And if you monitor that reservoir for a certain period of time, now I just use 10 years as an arbitrary amount of time, that is at the discretion of the regulatory agencies. And they're going to be looking at that very kind of with eyes wide open. If you can convince EPA or the state regulatory agencies that after you're through injecting, that you can close out a site at 5 years, 10 years, maybe it takes 15 or 20 years. Once you've demonstrated that to them, I think, there's a lot of, wherewithal there to say that probably your chances of having any long-term liability of that CO2 is very de minimis. Unless it gets into a legacy well that you don't know is there, it could come up in that well bore, that legacy well bore. But I think from the standpoint of just coming up through geology at a site where you've characterized very well and gotten a permit and followed all the permit requirements, your risk is very low.
Okay, great. And question from Gonzalo is the last one. In one of the first slides, you showed a graph that showed 40 USD per ton of the carbon capture costs. What capture technologies were analyzed? Solvents, or are these numbers aligned with your studies?
Yeah, so the main carbon capture media right now at scale is solvents. And there's a bunch of different solvents out there. Just keep in mind that you're using the solvents to strip the CO2, then you got to heat the solvents up. So you want a solvent that absorbs the CO2 readily, but allows it to release it readily at lower temperatures. And that's the inherent problem, is that you have laws of thermodynamics that you have to abide to with carbon capture. We're doing a lot of studies on solid sorbents. We're doing them on membranes, ionic liquids. We're putting catalysts in there that allow the CO2 to be captured at a lower heat rate and released at a lower heat rate. So there's a lot of different technologies that are kind of competing right now, but the only ones that are really prime time for commercial deployment are the solvents. And like the Boundary Dam is Fluor solvents, and the NRG site is MHIA KS1 solvents. And I suspect that most of the projects that are going to move forward at this point will be solvent projects.
Okay, it was a wonderful session. Richard, thank you very much for your time and patience to bring your knowledge and experience in this field to the table for other people. We are really blessed in Petrolern to be partnered with Southern companies on some of the initiatives. Thank you, everybody. Just don't forget our next talk would be next week, 12 May, on Unconventional Resources EOR by Dr. Tarek. Thank you very much all, and have a great weekend. Thank you.